We're good. Well, welcome this morning, and thanks for attending what's going to be a very interesting webinar entitled MACT Compliance. You might be closer than you think. I'm Bob McIlvaine, founder and president of the McIlvaine Company, and I'll be moderating this morning on behalf of Neundorfer Storm Technologies and United Dynamics Corporation. They're working together to help utilities and industrial companies develop pollution control and energy efficient strategies. This is going to be a big meeting this morning. We have 135 phones and a couple hundred people probably involved. So what we've done is initially to mute everybody except the speakers. However, we'll be unmuting all the phones after the session in about 30 minutes or so, and we encourage you to ask questions and to otherwise participate. So I'd like to start by introducing the four experts who will be talking about MACT compliance. A brief overview of what we'll be covering during this half-hour webinar. By the way, some of the noise you hear is people that are tuning in, and we're putting them on mute as they tune in. And Steve Ostanek is president at Neundorfer, and he's going to act as host. He'll be conversing with three other experts from Neundorfer, Storm, and UDC about factors in each area of the process that affect the existence, formation, or capture of pollutants regulated by the boiler MACT rules. Steve will first briefly introduce the concept of control, influence, and react as it relates to MACT compliance. He'll then talk with Jeremy Timmons, who's a chemical engineer at Neundorfer, about some things learned so far about MACT compliance through working with customers, and discuss coal characteristics and how this affects MACT pollutants. Next, Steve will speak with Dick Storm, CEO at Storm Technologies, about how fuel preparation and combustion impact MACT pollutants. Then John Kuvat, chairman of the board at United Dynamics Corporation, will talk about issues with heat transfer and how they affect the formation of MACT pollutants in the boiler. Then we'll be back to Dick, who will touch on the issue of air in leakage and how this impacts MACT pollutants. Finally, Jeremy will talk about back-end equipment and share insights about effective ways of capturing MACT pollutants. Following these conversations about the MACT pollutants, the panelists will stay on the line for follow-up questions and discussions. You can submit questions at any time during the webinar by using the chat feature as displayed up above there. Select answers from the list of participants and send in your comments or questions. Now, without further ado, I'll turn it over to Steve Ostanek from Neundorfer. Steve?
Thank you, Bob, and good morning, everyone. Our objective today is to learn more about what we can control, what we can influence, and what we need to react to in relation to pollutants regulated by MACT. Envision these as a series of spheres. What we control is very small and in the center. What we can influence but not control is a larger sphere. And what we have to react to but cannot control or influence is much larger. When we are creating strategies, such as for compliance, we are faced with this scenario and we have to understand what we really can control, influence, and react to. Jeremy, let's have you start by sharing some things we've learned so far from working with customers on MACT compliance projects.
Sure, Steve. We are currently involved in a few MACT compliance planning efforts. One of the initial steps in this process was to design and execute a baseline testing program that produces the information necessary for making future decisions. In reviewing some of these initial baseline results, many of the boilers were meeting or within reach of compliance on many of the MACT pollutants. This chart displays a summary of current MACT pollutant emissions: carbon monoxide, dioxins and furans, hydrochloric acid, mercury, and particulate from 11 of the boilers that we are currently evaluating. The colors indicate which boiler's level of compliance with each pollutant. Green means that they are well within compliance. Yellow indicates that the emissions levels are below MACT compliance with a little margin. Orange indicates that their current emissions levels exceed the future MACT limits. As you can easily see from the chart, this group of boilers has a serious problem with CO and dioxins and furans. About half of the boilers are near or above MACT mercury limits. The same can be said for the particulates. One thing to note is that boilers 4 and 5 easily passed all MACT emissions tests. We believe that some of the answers for improving the other boilers can be extracted from further analysis on these boilers 4 and 5. We believe that the MACT pollutant levels of boilers 4 and 5 are partly a result of superior combustion and optimal flue gas temperatures. For the other 9 boilers, we would first recommend a program to improve combustion. This program will reduce CO and DMF formation. It should also improve particulate and mercury emissions by reducing treated gas volume. The next step might be to look into any other improvements that can be made to the process to reduce the treated gas volume. These could be items related to improving the thermal efficiency or reducing air leakage. We might then recommend retesting the MACT pollutants.
Thank you, Jeremy. Understanding where we are now is important. We've seen in the example Jeremy gave us that we can uncover unseen opportunities or possibilities by creating a baseline testing program that gets us the right data. This baseline testing program is more than just a stack test. It's an integrated effort that seeks to understand the whole system, and the stack test is just part of it. Now let's go to coal preparation and combustion. Dick Storm, how are each of the MACT pollutants created, influenced, or controlled in the fuel preparation part of the system and during combustion?
Sure, Steve. Let's look at particulate matter first. If coal is not burned completely, carbon becomes part of the particulate matter that has to be treated. That's why coal fly ash is sometimes called refuse by boiler efficiency engineers. The refuse is both ash and unburned carbon. Coal fineness has a huge impact on particulate matter quantity and properties. High carbon and ash content is a problem for electrostatic precipitators, but I'll let you and Jeremy discuss that.
Dick, in what ways does coal fineness affect combustion?
Poor fuel fineness has at least 3 adverse effects on combustion. First, it affects the carbon in the ash. Secondly, it impacts flame carryover into the convection paths of the boiler. This can result in superheater slagging and fouling, draft losses, and other problems. Finally, because of delayed combustion and the resulting flame quenching, poor fuel fineness causes carbon monoxide production, or at least contributes to it. CO can be minimized by optimum particle size and fuel distribution. These are just fundamentals of good combustion.
So one thing, like fuel fineness, can have multiple effects on our process, which, as we know, then can have multiple effects on emissions. Dick, tell us more about best practices for optimizing combustion.
The furnace residence time for complete combustion is only 1 or 2 seconds. From this, it is easy to understand the importance of getting the inputs into the burner belt optimized. Finally, CO must be combusted in the furnace. Achieving low CO at the furnace exit is the start of reducing the formation of dioxins and furans. Excellence in furnace combustion can be measured by using a water-cooled HVT probe and extracting furnace flue gases to run through an analyzer. If the furnace is oxidizing, say 3% excess oxygen at all points, and the fineness is good, then the chances are that the CO will be very low. At Storm, I'd be happy to. Let's briefly discuss the importance of optimizing the inputs to the furnace. I'll share 4 points about this. First, most plants do not have good fineness on a day-to-day basis. When a push comes to a shove, operations will generally sacrifice fineness for pulverizer throughput. This is a simple fact of our experience. More fuel into the furnace can create more steam production to produce more megawatts, even if it is done inefficiently. Often the plant focuses on power production, not excellence in combustion. Secondly, when fineness deteriorates, so does fuel balance. Conversely, when fuel fineness is very good, so usually is fuel distribution. Good fineness by our definition is about 75% or better passing 200 mesh, and only 1 or 2 tenths of a percent remaining on a 50 mesh screen. So when fineness is very good, usually so is fuel distribution balanced to the individual burners. The idea here is to treat each burner like a cylinder in an internal combustion engine. We like to have in the range of plus or minus 10% to each burner. Poor fuel fineness can result in fuel distributions of plus or minus 25% and even worse. Thirdly, based on our long experience, we've developed our pretty well-known 13 Essentials of Optimum Combustion. These are a great start.
Dick, can you give us a quick explanation about the 13 Essentials?
Good idea, Steve. 9 of the 13 Essentials are pulverizer, primary air, fuel line, and classifier related. Fuel fineness, primary airflow measurement and control, classifier tuning, secondary airflow, and overfire airflow measurements and control remain vitally important. Proper airflow proportioning during load changes is a particular challenge with swinging loads, say where intermittent wind power supplies power to the grid.